quasi-classical. So we will be starting the session in next 5 to 10 minutes. We will wait for other students to join, and then we can solve the problems that we had in assignment 2. Okay, so we will start. We have waited for 10 minutes for the students to join, and so we will start the session of the day. Hello, hi, namaskar. I am Prashil. I am a Prime Minister's Research Fellow at IIT Mumbai, and here we are learning advanced thermodynamics and molecular simulations. Right, this is our week 4 live interaction session where we'll be discussing the solutions to the assignments that we have already submitted. Right, so let me just quickly go through the basics that we have covered. Right, so we started with thermodynamics. So we started with thermodynamics, right? And here we are applying mathematical framework. We are applying statistical framework. We are developing statistical framework to define the thermodynamics, right? Again, I'm giving you multiple times the examples. For example, if I'm having a system which is open system, this we have studied right already in our UG thermodynamics, that there are systems which are called as open systems, closed systems, and isolated systems. Right, this we have studied, and what it shows, okay, whether the energy exchange is possible and mass exchange is possible or not. So in open system, right, in open system we can exchange energy and mass both, right? This is what is the definition where we can exchange mass and energy with the surrounding. For example, I have a cup in which I have tea, right? So what is happening? The tea particles, water particles are going out. They are also coming in, right? So mass is exchanging and energy is also exchanging. That's why you see that the tea is getting cold when you keep at room temperature. Whenever it comes to a closed system, you see that for that cup of tea, if I put a plate on top of it, then what will happen? The mass transfer will stop, right? Energy transfer will be there. You will still see that the temperature of that tea is getting decreased, right? But mass is not transferred. Or simply example, I have a coke bottle that I took from fridge and it has been kept at room temperature. So what will happen? The particles of the coke are not exchanging, but energy is being transferred to the surrounding. So energy exchange is yes, and mass transfer is not there. And an isolated system, for example, for an isolated system where we are not exchanging energy and mass with the surrounding, that's why both are no. Now, what we are defining in this statistical framework, the physics based framework that we are developing for the thermodynamics, we are describing here qualitatively. Here also we will be defining qualitatively, but then we are using mathematics. So if the energy is exchanged with the surrounding, we will start with an isolated system. For an isolated system, energy is not exchanged with the surrounding, that's why energy is constant. So I will write E equal to constant. Then mass is also not getting exchanged with the surrounding, so number of molecules that are present in the system is equal to constant. And If I'm having, or I'm giving you an example of thermos which has water or a tea, right? The temperature will not decrease and tea will not evaporate, right? You will see the tea at the end of day also, right? So for that system, the volume of the thermos that we are talking about is also constant. That's why such systems are called as NVE systems, or we can also term it as microcanonical. Then come to the closed system where there is exchange of energy. So energy if exchange with the surrounding, what will be the variable that will be constant? You know, if a coke bottle I took from the fridge, if I keep it at room temperature, energy will exchange with the surrounding and temperature will be a constant value, right? That means energy exchange will happen until the temperature is constant. That means temperature is constant. Then number of molecules are not getting exchange, volume is also constant, so n is equals to constant, volume is also constant, and that's why this system is called as NVT system or canonical system. By the way, what is the meaning of canonical? You should search. It shows it's a common, something called as common. You just look after it. Then for an open system where there is exchange of energy and mass, with the system energy exchange will be there as I explained earlier to keep the temperature equal to constant, right? Mass transfer will happen until the chemical potential is constant, right? So mu is equal to constant, and then volume is again it is a constant value. Such systems are called as mu v t systems, or they are called as grand canonical. Right. And if I want to study the properties of such systems, what I need to do? I need to do observations. That means I can take snapshots at different time instances. Right, and those snapshots will be used to get the average properties of that system. Right, we can calculate the average properties using those snapshot. For example, if I want to know how the transition is happening in a system, for example, I have oil and water. So this is what is a mixture, right? This is a mixture. If I keep this mixture for long time, then what will happen? After certain time you will see, so if I want to see how the system is evolving, what are the equilibrium properties, I need to do I need to find out the properties, right? And for that I need to collect the snapshots. I need to take pictures at different times so that I can see how the transition is happening. And then I can track the particles, and then can be used to get the average properties of the system. Correct? Average properties can be calculated. Any doubt here? So the snapshots that I have taken, these snapshots, I can take snapshot after every 2 minutes, after every 3 minutes, right? I will define particular time interval to get the snapshots, right? To get the snapshots, and those snapshots will be used to get the properties. So that frequency I can set up after 2 minutes, or after 5 minutes, or after 10 minutes, and what is the maximum time. And then those snapshots can be collected, which are called as microstates. What do they call? As microstates. So those are called as microstates of a system. But you can see in this system, for example, this is a closed system. I did not mention earlier, but this is a closed system where there is exchange of energy, but there is no exchange of molecules. So you can see in this system, whenever it is transitioning, NVT are kept constant. That is, number of molecules are not getting exchanged. Volume is constant, and T is the temperature, which is also constant because energy is being exchanged with the surrounding. This is an NVT system. These are called as microstates. And here, since NVT are constant, right, in all the snapshots that I'm taking, so these are multiple snapshots, and whatever number of snapshots I'm taking for a particular system, those snapshots are called as microstates. But in all those snapshots, you will see the number of molecules are same. The volume of the system that I had drawn here are same. The volume is same, and since the energy is exchanged with the surrounding, the temperature is same, right? Temperature is same. That means these parameters are same, and that's why in all those snapshots something is common. That common thing is N, V, and T, and that's why the entire chunk of that snapshots, whatever is the number, 1,000, 10,000, lakhs, million, whatever is the number, that represents a macro state. So all those n microstates will be counted together, and that will define a macro state. So what is the difference between microstate and macrostate? Macrostate is a one big system that we are studying, and for to study those system, we need to take multiple photographs, multiple pictures of that system, right? And whatever number of snapshots, pictures you will be taking, those are called as microstates, right? That means if I want to study a property of a particular person, if I know I have a friend, I want to study whether he's staying in lab, or he's staying in the ground, or he's staying at some other location, I need to take multiple photographs of that person, and then I need to average out, okay, how many times that person was there on ground, how many times that person was there on in school, in class, in lab, right? And those snapshot will tell you what are the average properties of that particular person, right? Average properties of that particular person. But since we are studying only one person, that person is common in all those snapshots. That means that represents a macro state, that is a person under consideration, right? Person under consideration. So that's what we have seen. And then these macro states, Based on this macro states, we were calculating something called as w is number of ways in which we can distribute the energy particles in the system, right? And using that w, we optimize the w to get the free energy in terms of partition function, right? That's what we saw. So now based on this we will be solving some questions. Okay, so the first question is there on your screen. Please try to solve this question. It's a very simple question that we already know from our undergraduate thermodynamics, right? We already know these things from our undergraduate thermodynamics. What are the state and path functions, right? Correct. So we'll just go through. So we know that I have an initial system is, and I want to go to a final system that is fs. In your undergraduate studies, you must have seen PV diagram from initial system to final state, initial state to final state. If I want to go, I have multiple ways, right? I can go by this way. For example, the red one that I had drawn, I can go by this way or I can go by this way, right? So here you can see, if I go by this way, then it is constant volume, then it is constant pressure, and if I go by the other way, then it is constant pressure, constant volume. Anyways, I'm going to go at the final state. So there are multiple paths in which I can go from initial state to final state. Understood? Now if I go from initial state to final state, what are the properties that depend on state are called as state functions, and what are the properties that depends on the path are called as path functions, and we need to understand, right? So we know that entropy, work, heat, and gives free energy, these are the properties, and we need to tell what and all as the state functions, right? So we must have you must have seen that we can write delta h is equals to delta u minus t delta s, right? So what does this tells? It is h2 minus of h1, u2 minus of u1 minus t into s2 minus of s1. Why we are writing? Because you can see this delta s, whatever is the change, can be written in terms of only the initial, that is first, and final state, that is second. Entropy can be written like that, correct? Gives free energy is also written like that. Delta G is equals to delta H minus T delta S, right? Correct? That means here delta G can also be written as G2 minus of G1. So this is a path function. So entropy and energy are the path function. On contrary, if I say work and heat are the path function, why? Because they depends on the path that I am taking. Correct. Now if I am standing here, and if I want to go to the next floor, if I go by lift, work done will be different, and if I go by stairs, work done will be different, right? That means it depends on the work, and heat that my body is releasing is also different. That's why heat and work are called as path functions, whereas the total energy is only the difference of initial and final state, that depends on the state only. That's why they are called as state functions, right? So state function versus path function. So which of the following is a state function? So work and heat are the path functions. So the state function is entropy and Gibbs free energy, right? Entropy and Gibbs free energy are the state functions. So that is the answer to question number 1. Okay, so please let me know if there are any doubts. I'll be here to explain the things, right? Going to the next question, you can see this is what is the first law of thermodynamics, that is what is defined over here. Please try to solve it. Right, so the question is, if heat is added to the system and work is done by the system, then the change in the internal energy of the system is given as. We know the first law, that the total energy of an isolated system is constant, it is not changing, is equals to Q plus W, right? And what are the conventions? If heat is added to the system, then the energy of the system increases, internal energy changes, right? That's why we are considering it as a positive. Opposite is the negative. Similarly, if I do work on the system, if I do work on the system, then energy is added to the system, internal energy increases, right? That means it is a positive quantity. Now you just tell me, if heat is added to the system, that means Q is positive, and work is done by the system, that means W is negative. So delta U is equals to Q minus W. Option B is correct, right? Option B is correct. Solution to the question number 2. Easiest question, right? Moving on to the question number 3. Which of the following are the conjugate variable? Conjugate variable you need to identify. Please identify. So what question is asking you? Which of the following are the conjugate variables? So we know the equation that we have. The fundamental equation for an isolated system, du is equals to tds minus of pdv plus mu dn, right? So from this equation itself you can tell what and all are the what and all are the conjugate variables. We know you can translate this so that we can get. No, that's also possible the other way, that ds is equals to du, ds is equals to du by t minus plus p by t dv minus of mu by t dn, right? And now I'll just tell you what are the conjugate variables. You can see these pairs are called as conjugate variable. Now we need to find out the answer. I'm exchanging the volume with the surrounding to keep the pressure constant, right here. Or if the pressure is constant, if the pressure is varying, then I'm keeping the volume constant. Pressure is varying, that means volume is constant, correct? So these are the conjugate variables. So do you see those pairs? Temperature and entropy, yes, temperature and entropy is there. Option D is correct. Then volume and temperature, no, they are not. Pressure and volume, yes, they are conjugate variable. And temperature and pressure, they are not conjugate variable. So option B and D are correct. B and D are correct option. So this is the question number 3. Please let me know if there is any doubt. I am here. Then there is question number 4. Please try to solve this. So the question is on your screen. Use the fundamental equation and then derive. Right? So first of all, you should write down the fundamental equation that we wrote in previous question. Du is equals to TdS minus of PdV plus mu dn, and then you have to convert that into some other. So it is saying one component system, that means only one component is present, so dn, that is change in this, will not be there, it is pure component. So we can just write du is equals to tds minus of pdv. Now you do the Legendre transform, so this is equals to sdt, correct. Gives free energy is at constant temperature and pressure. So already this is temperature is controlling variable, and here it is vdp, and that is equals to dg. So now you can see, when temperature and pressure are the controlling variables, then delta g is your free energy, that is gives free energy, right. So dg is equals to minus sdt minus of, no, d minus of sdt is here, then plus vdp is here, right. So total b is the answer to the question, minus sdt plus vdp, right. Minus sdt plus vdp is equals to the answer, right. Question number 4, option b is correct. The change in the Gibbs free energy of a one component system is given by equation b, right. Try to solve question number 5. Now what we did in the last question, similar we have to do here. Entropy and pressure it is asking, and what is the, so do the Legendre transformation of a fundamental equation and obtain entropy and pressure. See here it is volume, you have to change this, correct. You have to change that value, and then you find out what is the case, right. Temperature, entropy should be there, is equals to this. So entropy and pressure is there, and what is this function, I don't know, that we have to find out, correct. Substitute the value of tds. See here you can see d of comma v, right. That means d of q, this has to be plus because we did Legendre transformation, this also plus, this also plus, this is equals to q plus pv, that means dh. So this has to be dh, that means your whole Helmholtz free energy is something that defines, that is a free energy and is an energy function when entropy and pressure are the controlled variables. So option c is correct, option c is correct, entropy and pressure. Just a minute. Not option C. H stands for enthalpy. So enthalpy is this. H stands for enthalpy. So whenever I'm having entropy and pressure, it is and it is the H, right? Correct. Question number 5. Now question number 6. Solve it. This is something that we can calculate using the fundamental equation. Again, the first equation that we wrote, it's the same, right? And there from there you just calculate. So the fundamental equation, what does that say? Right? Isolated system, so I can consider or write it as S is equals to du by t plus p by t dv minus mu by t dn. So you can see for an isolated system, energy is constant, volume is constant, number of molecules are constant, and for such system, it is the entropy, and it has to be a maximum value, that is the equilibrium state. So option A is correct. Option number A is correct, right? This we also know from the second law, which says that energy is constant, that's why it cannot be the driving force for a change that is being happening in an isolated system, and there has to be some property that is having a gradient which causes the change to happen, right? And that's why it says that delta s should be greater than or equal to 0, and that's why maximization of the entropy is something that is warranted for a process to happen, right? Then question number 7: which of the following variable is not an extensive variable? Entropy is something that changes with the system. If I double the system size, entropy doubles. Internal energy is also dependent on mass. Gibbs energy is also dependent on the mass. But what is chemical potential? It is partial molar Gibbs energy, right? Delta U by delta N at constant temperature and pressure, right? So you can see it is divided by number of molecules. That means per unit molecule. So it is an intensive property. Intensive property. So chemical potential is not an extensive variable, it is an intensive variable, right? So option A is correct here. Option A is correct. Next question is, which of these are or is not homogeneous function of x and y? What is meant by homogeneous function? We know that in any function, if I substitute instead of x lambda x and lambda y, then we should get lambda times function x comma y, then it is a homogeneous function. Now we just substitute the values over here, x plus y, right? Lambda x lambda y, I can get lambda x plus y, that means lambda times f of x is possible. Homogeneous function, lambda xy is equals to, so I'll substitute instead of x lambda x, instead of y lambda y, so it is lambda square xy, which is equals to lambda squares f of x comma y. That means it's an homogeneous function. So these three are homogeneous function, you can see, right? By mistakenly it has been written like this, so it has to be x to the power y. So when I am writing lambda x raised to the power lambda y, I do not get lambda time f of x comma y, so it is inhomogeneous function. Second is x lambda x lambda y plus 2, so here also I cannot take out lambda common and it is not equals to this, and that's why these two, option number C and D, option number C and D is correct answer. These are not homogeneous function, right? Not homogeneous functions, right? So this we had discussed in detail in the class. And now question number 9 is there on your screen. You have multiple choice questions. There are 100 questions. Every question has 4 choices, right? A, B, C and D, just like what we are doing right now. We are solving 10 questions. It is asked for 100 questions, right? And each of the question is having one or more correct choices, and that choice can be correct or false. Now if you randomly solve the questions, what is the most probable number of correct answer? How many correct answer that you are supposed to get? That you have to calculate. Please try to solve it. I'm here. We can solve the question together later on, right? So Please try to do it. Right, so we will be solving the question here. So for each question there are four options, and out of those four options, maybe four, maybe five, whatever number of options can be correct, right? So for each correct questions there is 50% probability, right? Either it is true or false. So what is the probability of correct answers if I guess the answers? So we know that there are four questions, each of there are 100 questions, four options for each. Either of them can be, p of a can be correct, right? So for a question p of a and p of b and p of c and p of d, right, there are multiple options that can be correct. That's why it's connected by and this and this and this. A and b and c, a and b, b and c, c and d, what and all are possible options. So these are all connected by and. So these many probabilities are there, and this is giving you the total probability of having the correct answer, right? So each of them are having a probability, and it will be 2 1 by 2 raised to the power 4, right? If 50% probability is there for each correct answer, then this is the value for one question. Similarly for 100 questions, what is the probability? So it is 100 divided by 16, which comes out to be close to 6, right? 6.4 something is there, right? 40. So it is close to 6. That the most probable number of correct answer would be 6. So out of those 100 here, there are chances that you may get 6 correct answers. In the last question, which is on your screen, it is very easy question. Please try to do it on your own, else we'll solve together. Let us try to solve this question. So let us solve this question quickly, which is the last question of the day. It talks about the approximation, Stirling's approximation for a very large number. We know ln of n factorial is equals to n ln n minus of n. That means ln of 10,000 factorial. Instead, just keep it as it is. N factorial is equals to exponential n ln n minus of n. This has to be there. Now n is equals to 10,000. Do you see any options with exponential term? No, right? That means none of this answer is correct. Actual answer will be, you substitute this value and that will give you the Stirling's approximations for the given factorial number. Right? So please, so this was the last question. So I'll just go through all the questions. First question, which was talking about the state versus path function. Second question talks about the first law of thermodynamics. Then it talks about conjugate variable. Next question, right? If pressure changes, volume is constant. If number changes, that means chemical potential is constant, and so on, right? Conjugate variable. Then what is a fundamental equation when temperature and pressure is constant, right? How can we define that in terms of Gibbs free energy? Then question number 5, it is also asking equation that defines the energy function. What is that energy function when entropy and pressure is constant? So it is enthalpy. Then sixth question is an isolated system. What is something that drives the process to happen in an isolated system? It's the entropy. Then question number 7, it talks about the extensive versus intensive variable, and we know that the chemical potential is normalized factor, and that's why normalized by some factor, and that's why uh, the chemical potential is the intensive property. Then we have checked what and all are the homogeneous and heterogeneous functions. In question number 9, we talked about the probability, right? And then lastly, these Stirling's approximation. So that's all for the class that was scheduled today, and I'll be here and I'll be answering the questions if you have any doubts. So please let me know. Right? So we will stop this session here, and then we will meet in the next class. Thank you for joining. We will meet next time in next week on Tuesday. Thank you.